In the last lecture, we looked at how temperature can influence how fast or slow a reaction occurs. In this lecture, we're going to look at some other ways to impact how fast or slow a reaction will proceed by using what's called a catalyst or inhibitor. So getting into it now, we're really continuing to ask the question of how do we change the rate of a reaction. Okay, that's a really important question. And so we've looked at temperature. So temperature, and most often it's the case that heat will increase rate. So if we increase heat, we increase rate. If we decrease the temperature, that is cool the reaction, decrease the amount of heat that we're inputting into the system, we will decrease the rate, relatively speaking. Okay, so we looked at that last time. But another way is to answer this question of how do we change the rate of a reaction is to add a catalyst or inhibitor. Okay, and these are two agents and they are sometimes called reagents. Then they're not reactants by definition, but I'm not going to worry about that definition in the class. They're just two chemicals that we add to our chemical process, that change or influence the speed of the reaction, which is also called the rate of the reaction, by changing activation energies. Okay, so that's kind of the principal thing that catalysts and inhibitors do. Now, for those of you that have seen this before, you know there's something about how they're consumed / regenerated that we need to get to. But the focal point is going to be on energetics. And that is going to be, if we're going to speed up the reaction, we need to influence the activation energy, because that's what controls how fast or slow a reaction is. And so catalysts, going off of this, catalysts speed up the reaction. That is to say, they increase the rate. So maybe that's a slash. Increase the rate by decreasing the activation energy. Speed up the reaction or increase the rate by decreasing the activation energy. Now, conversely, inhibitors do the exact opposite. Inhibitors slow down or decrease the rate of a reaction by increasing the activation energy. So, how do we change the activation energy? Well, I suppose if we're going to be really precise, there are a large number of ways that we could change the activation energy. But in general, if we focus on what the activation energy is, so the ways to change the activation energy will actually be a little bit simpler. That is to say, if we're trying to figure out the ways to change the activation energy, we can remind ourselves that the activation energy is simply the energy difference between starting material and transition state. Okay, so with this in mind, if it's the energy difference between the starting material and the transition state, the ways that we could change the activation energy are, we could change, I'm going to write it this way, that is to say, changing the starting material and, or you could do both, I guess, and or transition state free energy will cause the activation energy to change. Okay, so a way to change the activation energy is to change the free energy of the transition state or the starting material. So a catalyst will, okay, first of all, let's remind ourselves what a catalyst does. It speeds up a reaction by decreasing the activation energy. It will decrease the transition state free energy, okay, or it could increase the starting material free energy. If you increase the starting material free energy, you will decrease the activation energy. Maybe what we do is we look at that. So let's say we've got some starting material in some product, and we're considering a reaction that looks like this, okay? What I'm saying is that if this is the transition state uncatalyzed, without a catalyst, what we could do is we could introduce a catalyst, and that would decrease the energy of the transition state. So now our new reaction has an energy that looks like this. And so this is our new activation energy. Whereas our old activation energy, it's right here, and that original activation energy was higher, so the reaction proceeded more slowly. When we added the catalyst, we decreased the transition state energy in this particular example, and that decreased the activation energy because the starting material remained the same. And so now the difference in energy, because that transition state was lower in energy, is now smaller. And so the activation energy, which is equal to that difference in energy, is smaller. And so the reaction is faster because the activation energy, recall, is that barrier for a reaction to occur. Now, I'll try to draw this a little bit bigger this time. What if we consider a reaction where the starting material changes? So if this is our transition state, this is our starting material, and this is our product. Another thing that you could do is you could change the starting material energy. Now, in this case, what you want to do is make the starting material higher in energy. This is the same as saying the starting material is now less stable with the catalyst present. So this is actually starting material plus catalyst. I'm actually, for those of you thinking more deeply about kinetics, I'm skipping a step where we let those form an adduct, and then the starting material now can more readily get to the transition state, because it's all about the difference in energy between that ground state and our transition state structure. And so the activation energy is now smaller. And if that activation energy is smaller, we get to a faster reaction. Often it's the case that in a catalyzed reaction where a catalyst is present, there's a combination of both of these things that's occurring. That is, you are increasing the energy of the starting material and simultaneously decreasing the energy of the transition state. Let's say that a different way. So what I want to recall, recall that stability is related to relative free energy. So stability is related to relative free energy. And we say that higher energy things are less stable. Higher energy things are less stable, and lower energy things are more stable. The bowling ball is higher on top of the shelf. It's a less stable situation than the bowling ball being on the floor, which is a more stable situation. Okay, with this in mind, a catalyst will often do both of the things that we talked about previously. That is, it will operate on the starting material and the transition state free energy. So a catalyst will often stabilize the transition state, and that will decrease the TS free energy. Similarly, it will destabilize the starting material. So we'll take that starting material and start to stretch it and contort it a little bit so it gets a little bit closer to the transition state energy. Both of these things, increasing the starting material, if we're starting here, let's see, I don't know which way, sorry, the camera's a little off. This is my transition state and this is my starting material. I don't know how to do the mirror mode and zoom, sorry. Anyway, so what we're doing is we're bringing up the starting material energy and bringing down the transition state energy to make the barrier or the activation energy or the barrier to reaction a lot smaller. So the reaction's a lot easier to, is a lot more likely to occur. And if the reaction's a lot more likely to occur for a population of molecules, the number of those molecules doing the reaction, climbing over the barrier per unit of time increases, and that results in an increasing rate. Okay, so we destabilize the starting material, we stabilize the transition state. If we destabilize the starting material, we increase the starting material free energy. So this is how catalysis works. Those that want to look more deeply into kinetics, and it's a really good thing to do for society, would say, you know, the starting material actually forms an adduct with the enzyme in an initial step in our reaction to give an intermediate structure that's higher in energy. And yeah, that's certainly true. Okay, so what we can do is we can then focus on an intermediate. So, or excuse me, an inhibitor. We'll get to an intermediate in a second. So an inhibitor will do the opposite. So an inhibitor will slow the reaction. And I say will often, it will always slow a reaction. Otherwise, it's a catalyst if it speeds up a reaction. So it will slow the reaction by doing the exact opposite of what we said before. It will destabilize the transition state and increase the TS energy. Likewise, it will stabilize the starting material, and that will decrease could do a better job there writing the word decrease the energy of the starting material. So an inhibitor works in the exact opposite way as a catalyst. It influences the rate of the reaction, to be sure. It doesn't just leave the reaction alone, it influences it by usually both destabilizing the transition state and stabilizing the starting material. Both of these will result in an increase in the activation energy, or a higher barrier for the reaction to occur. That means fewer molecules per unit of time are able to climb over the barrier. So looking at an inhibitor, will influence the energy diagram by increasing the activation energy. So it's the activation energy that's increasing in this way. In this case, when an inhibitor is being used, most often it does two things, where it influences the starting material free energy and the transition state free energy. However, we could just focus on one thing at a time. So if we've got our reaction coordinate and our free energy, okay, what we could do is we could start by considering our starting material, our product. We've got our original activation energy. And then what we could do is we could introduce a new transition state, or we will introduce a new transition state when the inhibitor is added to the reaction, and that's going to create a new energy diagram. The reaction is still spontaneous, but it suffers from a much slower rate because the activation energy, which is the difference between the starting material and the transition state, is now larger. Okay, so we've operated in this case on the transition state only. We could do the exact same thing on the starting material. Okay, so we have one transition state, and here the transition state energy is not going to change. But let's say we stabilize the starting material, bring the bowling ball from the shelf to the floor. This is now our starting material with our inhibitor. We have to climb a much higher barrier. It's the same transition state, but we have to climb a much higher barrier for the reaction to occur. And then this larger difference now is our activation energy. Okay. So there's another aspect of all of this that I know people that have thought about catalysts really want me to get to, and really think I should get to. It's this idea of when you add a catalyst to inhibitor, something special happens in that people like to say that the catalyst and inhibitor are not consumed. That is, if you've got a catalyst, like a very common catalyst is an enzyme, you really only need one enzyme, and assuming it assuming it works forever, it doesn't kind of like denature or kind of die, and during the course of the reaction can kind of continue onward forever, because a catalyst, by many people's definitions, is not consumed. So are catalysts consumed during a reaction? Many people will say no. So many people will say no, they're not consumed. Okay, so I should be careful here, because I want everybody to do well in all their classes. And so if you have an instructor that says the catalyst is not consumed and they want you to provide that definition of a catalyst, something that speeds up a reaction and is not consumed, that's fine. That's not truly what happens. And so if you actually like dig into the literature and read some of the most thorough definitions of a catalyst, and I think it is important to bring up, which is why I'm doing it, there's an idea that a catalyst is actually always consumed. So unfortunately, if you really want to get into it, a catalyst is always consumed because it interacts with the system. We have a chemical reaction, and that reaction is interacting with a system. And so, yikes, what that means is, is that it's not truly correct to say a catalyst is never consumed. But there's some redeeming, there's some redemption here. A catalyst is always consumed, but it's nearly always regenerated. Okay, so it's here's the issue. People like to say that a catalyst is never consumed. So they'll say, okay, definition of a catalyst in some class is going to be something that speeds up a chemical process, a chemical reaction, and is never consumed. It's a really fun definition to say because it's a really kind of surprising thing to have add something to a chemical reaction and see it never be consumed. The reality is, for a catalyst to work and operate on a system, it must always be consumed. Otherwise, if it's not consumed, it's not doing anything. If you just add it to a reaction and it's not consumed, it's not impacting the system at all. It's not stabilizing a transition state or destabilizing a starting material to make a reaction faster. So it's always consumed, it's just always regenerated. And so the best definition is a catalyst promotes a reaction by increasing its rate and it's both a starting material and product. Okay, so that's where it's this last line, which is where people like to say it's not consumed. Okay, and so what you get is you would have starting material plus cat. Now, cat with a period is the abbreviation for catalyst. If you forget the period, you've just written the word cat, and so you're describing like a mammal. I know it's funny, but it's, you know, details are important. So basically what we're saying is starting material plus cat gives rise to product plus cat. Okay, so that's truly what happens. Now, I think it's an important distinction because there are many times that we pump in some catalytic atoms as starting materials, and they're catalytic, so they promote the speed of a reaction. But if we do the reaction, we get those catalytic atoms back, but they're not the same catalytic atoms that we put in. Let's say it a different way. There are many times where H plus on its own will be a catalyst for a reaction. So you add in some H plus to the reaction, and it's both a starting material and a product. But here's the problem. The product H plus is not the exact same H plus atoms that you put into the reaction. So if I put some H plus atoms in and I labeled them by some labeling form, I would not get labeled atoms out in many cases for an acid catalyzed reaction. And people get really hung up on, is it truly a catalytic reaction? Well, it's still doing everything that a catalyst does. It's both a starting material product and it's increasing the rate of a reaction. Now, similarly, what's great, another thing that comes out is in some of the best catalysts in the world, which are enzymes, if it's true that they're never consumed, then why do they die? That is, if you put enzymes into a system, enzymes are very powerful catalysts, but they have a lifetime before they just kind of crash and burn, literally crash out of solution as a bunch of biological gunk. And you have to kind of add new enzyme to get the reaction kickstarted again. Now, enzymes are quite efficient. I'm just saying, like, if they do their job, it's sometimes hard to recover the enzyme. Well, the reason why they die is because they're consumed and regenerated, regenerated over and over and over and over and over again. But they're also very fragile molecules. And during the process of being consumed and regenerated, some things are going to start happening. They're going to do what's called misfolding and denaturation as they start to break down a little bit. There's still just a long chain of amino acids, if you know what a protein is. But in terms of catalytic activity, they're no longer serving as a good catalyst. They're just a non-participating molecule. So that distinction is important to me. But being a catalyst, a starting material in a product means even though it is consumed and then regenerated, okay, even though we don't get to say it's not consumed, we don't get to say that anymore. Something that's special about a catalyst is we can use small amounts, that is substoichiometric amounts, of catalyst. This is very exciting. This is why people get excited about the idea of a catalyst not being consumed. We're all saying, you know, you might be sitting there being like, I feel like everybody's just saying the same thing. We're all just very excited about the fact that we have these very powerful molecules that accomplish something really helpful for us. They get the bowling ball lifted a little bit higher up so we don't have to put as much energy into the system to get it over the wall, or they decrease the height of the shelf. Those are really helpful things. But because they're not, they're both a starting material and a product, we can use substoichiometric amounts, which means we can use a small amount of catalyst. Now, for example, in an acid catalyzed reaction, we could use 1/10 or 0.1 moles of acid per 1 mole of starting material. That's wonderful, okay? Because acids, as you know, can be hazardous to work with. So if we set up a 1 mole of a reaction, which is a fairly big scale, let's say we've got a big liter of starting material and we want it to go into product, okay? We don't have to add a liter of catalyst. That is, say if we have 1 mole of starting material, that's a better way of thinking about it. We don't have to add 1 mole of catalyst to get it all to product. We could add 0.1 moles, much smaller amount. So if it's like they have the same molecular weight and they have the same density, we could say that if we had a liter of starting material, a big liter bottle picture, we could add maybe 100 milliliters, and even in some cases, even less than that. For example, enzymes can operate at 0.0001 mole loading. 0.001 moling. That means at 0.01%. So if you have 1 mole of starting material, you could be down to 0.0001 moles or 0.1 millimoles of catalyst being added, which is great because then we don't have to spend a lot of time, money, and resources developing these catalysts. Okay, I knew I wanted to get into intermediates in this lecture, but I think I'm going to wait until the next lecture. We're going to pick up with intermediates and how it relates to energy diagrams in the next lecture.